In this presentation, we have to talk about Lorentz gauge. For that, consider the Maxwell field equation. Div D equal to rho. You know the value of displacement vector D equal to epsilon naught into E. Therefore, this equation is modified as div E equal to rho by epsilon naught. The value of E is minus grade pi minus dou A by dou T. We have expressed E in terms of scalar and vector potentials. Now this is del dot minus grade pi minus dou A by dou T equal to rho by epsilon naught. This is del square pi plus dou by dou T of del dot A, which is equal to minus rho by epsilon naught. Just I have multiplied all the terms by negative sign. With this equation, we have to carry out one operation. Del square pi minus mu naught epsilon naught dou square pi by dou T square. This term is subtracted and add the same term, my plus mu naught epsilon naught dou square pi by dou T square. Then write down the term plus dou by dou T of div A, which is equal to minus rho by epsilon naught. If you simplify this, you can get del square pi minus mu naught epsilon naught dou square pi divided by dou T square plus dou by dou T of, just take this dou by dou T as a common term and combine these two terms. Del dot A, already we have taken out this dou by dou T, so del dot A is present. Here mu naught epsilon naught plus mu naught epsilon naught dou square pi by dou T square is present. Already we have taken out one dou by dou T, and the rest of the term is dou pi by dou T, which is equal to minus rho by epsilon naught. See, this is mu naught epsilon naught is our 1 by c square. Therefore, the above equation is modified as del square minus 1 by c square dou square by dou T square into pi plus dou by dou T of del dot A plus 1 by c square dou pi by dou T, which is equal to minus rho by epsilon. This is equation 1. In this equation 1, consider this term. Already we have proved that div A plus 1 by c square dou pi by dou T equal to 0. This is our Lorentz condition. This is called Lorentz condition. If equation 1 satisfies the Lorentz condition, that means del dot A equal to minus 1 by c square dou pi by dou t. This is our Lorentz condition. See here, div A plus 1 by c square dou pi by dou t equal to 0. This is our Lorentz condition. If equation 1 satisfies the Lorentz condition, what is the value of div A? Div A equal to minus 1 by c square dou pi by dou t. So instead of this term, del dot A, we can put minus 1 by c square dou pi by dou t. So the entire is 0. The second term is discarded. Then the above equation is reduced as see, this equation is modified as del square minus 1 by c square dou square by dou t square, entire is operating on pi equal to minus rho by epsilon naught. Say this is equation 2. See here, in equation 1, this is our div A plus 1 by c square dou pi by dou t. If equation 1 satisfies the Lorentz condition, this could be equal to 0, which means that div A equal to minus 1 by c square dou pi by dou t. If equation 1 satisfies Lorentz condition, automatically the value of div A is minus 1 by c square dou pi by dou t. If you add minus 1 by c square dou pi by dou t plus 1 by c square dou pi by dou t, the term is vanished. So we can get the equation of this form. This is our D'Alembert operator. That is operating on pi, which is equal to minus rho by epsilon naught. This is identical with our Poisson's equation. So here del square is our Laplacian operator. Del square minus 1 by c square dou square by dou t square is our D'Alembert operator. If the D'Alembert operator operates on scalar potential pi, you may get minus rho divided by epsilon naught. This is identical with our Poisson's equation. Now we have to get the same Poisson equation with the help of our vector potential. For that, take our Maxwell's field equation. Curl H equal to J plus dou d by dou t. You know that del cross H equal to J plus dou d by dou t. Then del cross mu naught into H equal to mu naught J plus mu naught dou d by dou t. Just I have multiplied all the terms by mu naught. Mu naught into H is our B. It is curl B equal to mu naught J plus mu naught epsilon naught dou E by dou t. You know that D equal to epsilon naught into E displacement vector. This is del cross curl A. If div B equal to 0, then B equal to curl A. Here A is our vector potential. This is equal to mu naught into J plus mu naught epsilon naught dou by dou t of the value of E minus grade pi minus dou A by dou t. The left hand side you have to use our vector identity. Del cross A is grade of div A minus del square A. This is vector identity. which is equal to mu naught J. See here, minus mu naught epsilon naught grade of dou pi by dou t. Just I have operated this to the bracket, minus mu naught epsilon naught gradient of dou pi by dou t, then minus mu naught epsilon naught dou square A by dou t square. Now bring all the terms to the right hand side. This is del square A minus grade of div A plus this term mu naught into J, then minus mu naught epsilon naught grade of dou pi by dou t minus mu naught epsilon naught dou square A by dou t square equal to 0. Now we have to simplify this further. Align these two terms, del square A minus mu naught epsilon naught dou square A by dou t square. See, del square A minus mu naught epsilon naught dou square A by dou t square. Take this minus gradient outside. Minus gradient of, this is nothing but a grade, minus gradient. Then write down the rest of the term, div A. We have taken out minus gradient outside, so this is plus mu naught epsilon naught. Plus mu naught epsilon naught dou pi by dou t. The only left out term is mu naught into J. Shift the term to the right hand side, which is equal to minus mu naught into J. See here, these two terms are combined. Then take this gradient. This is nothing but a gradient operator. Minus gradient outside, div A. We have taken out minus gradient outside. So this is plus mu naught epsilon naught into dou pi by dou t. Finally, we have shifted this term to the right hand side. Now, it should be modified further. In this equation, if this equation 4 is satisfying the Lorentz condition, say this is equation 4, if 4 satisfies the Lorentz condition, you know the Lorentz condition, div A equal to minus mu naught epsilon naught dou pi by dou t. This is our Lorentz condition. That means div A plus mu naught epsilon naught dou pi by dou t equal to 0. If 4 satisfies the Lorentz condition, instead of div A we have to put minus mu naught epsilon naught dou pi by dou t. So the terms available inside the bracket is 0. Automatically this equation is reduced to del square A minus mu naught epsilon naught dou square A by dou t square equal to minus mu naught into J. This is del square Laplacian operator minus 1 by c square. Mu naught epsilon naught is our 1 by c square. Then dou square by dou t square. Entire is multiplied by A equal to minus mu naught into J. There is real inversion operator operating on the vector potential equal to minus mu naught into J. Already we have proved real inversion operator operating on the scalar potential equal to minus rho by epsilon naught. These two equations are identical with our Poisson's equation. Now we have to prove the invariant of the Lorentz condition and our Gauge transformation. For that, take the Lorentz condition. You know the Lorentz condition is div A plus 1 by c square dou phi by dou t equal to 0, or div A plus mu naught epsilon naught dou pi by dou t equal to 0, both are same. Here replace A by means of A dash minus grade lambda and pi by means of pi dash plus dou lambda by dou t. These two are called Gauge transformations. Here lambda is our Gauge function. Instead of A, we have to substitute A dash minus grade pi. Del dot A dash minus grade lambda. Instead of A, we have to substitute A dash minus grade lambda plus 1 by c square dou by dou t of pi should be replaced by pi dash plus dou lambda by dou t equal to 0. This is our del dot A dash minus del square lambda plus 1 by c square dou pi dash by dou t plus 1 by c square dou square lambda by dou t square equal to 0. Now align these two terms. Del dot A dash plus 1 by c square dou pi dash by dou t. Then shift these two terms to the right hand side, which is equal to del square lambda minus 1 by c square dou square lambda by dou t square. See this expression. If Lorentz condition is invariant under Gauge transformation, if Lorentz condition is invariant under Gauge transformation, the Gauge function should obey the relation D'Alembert operator operating on lambda equal to 0. See here, lambda is the Gauge function. If the Gauge function satisfies the relation D'Alembert operator operating on lambda is our Gauge function equal to 0, then Lorentz condition is invariant. What is our Lorentz condition? Del dot A plus 1 by c square dou pi by dou t equal to 0. Now we have transformed a into a dash, pi into pi dash. Even though the Lorentz condition is invariant, there is no change in the Lorentz condition. If the lambda, that means gauge function, should satisfy the condition of D'Alembertian operator into lambda. That means when the D'Alembertian operator operates on lambda, the right hand side should be 0. Therefore, in this above relation, if the right hand side is 0, if this term is 0, then del dot a dash plus 1 by c square dou pi dash by dou t equal to 0. In the above equation, if del square lambda minus 1 by c square dou square lambda by dou t square is equal to 0, then the Lorentz condition is invariant. Once again we can get our Lorentz condition. That means in terms of a dash and pi dash, Lorentz condition is initially expressed in terms of the vector potential A and the scalar potential pi. If it is subjected for gauge transformation, we can get this condition on the left hand side. Del dot a dash plus 1 by c square dou pi dash by dou t, which is equal to del square of lambda minus 1 by c square dou square lambda by dou t square. If del square lambda minus 1 by c square dou square lambda by dou t square is equal to 0. This is nothing but our D'Alembertian operator operating on lambda. If this condition is satisfied, then del dot a dash plus 1 by c square dou pi dash by dou t equal to 0. Hence, we have proved that the Lorentz condition is invariant under gauge transformation. The necessary condition is the D'Alembertian operator. When the D'Alembertian operator operates on the gauge function, we can get 0 on the right hand side. If this condition is satisfied, then our Lorentz transformation is invariant. Now we may say the potentials belonging to this special category are said to be in Lorentz gauge.